Hi everybody, welcome back to the lecture Computer Animation. Today about rough interpolation and subdivision. So first to rough interpolation, which is a completely different kind of interpolation. So far we wanted to have a smooth interpolation between control points, which is good to model smooth surfaces. But if we want to model something rough like a mountain or a snowflake or even clouds in the sky, we don't really want to have a smooth interpolation, but something rough like those. So this is interpolation not for a smooth surface, but for a rugged surface. In an example here are fractals, for instance the Koch snowflake, which you can see here. So here you can also see the interpolation rule. You start with two control points at the ends and you have a straight line, and then you subdivide this line by inserting this triangle here in the middle, right? So you basically cut at 1/3 and 2/3, and then you have length of 1/3 here for the line, and here correspondingly you have length 1/3 lines which make up this triangle. And then you have 1, 2, 3, 4 lines, 4 new lines, and for each of those 4 new lines you can do the same thing, right? Replace this line by a line with this triangle in the middle, and so on, right? And you can do this recursively. So each time you get straight lines and you replace those straight lines by straight lines with a triangle. And if you continue, you get kind of this snowflake shape. Yeah, fractals, they use a formula. So they don't use lines, but here you assume that you have a surface or a two-dimensional coefficient space, and this coefficient space is interpreted as the complex plane, right? So the x-axis would be the real part of the number and the y-axis would be the imaginary part of a number. And on this complex plane you then do this iteration. So you start with some starting point c, which is a complex number, and you start with z0 equals 0, and then you compute the next z according to this iteration. So for z1 you would have z1 equals z0 square plus c, so that would be just c. Then you would have z2 equals z1 square plus c, so that would be c square plus c, and so on. And you can see that depending on the starting point of this c, your iteration will either converge, meaning it will not grow anymore after some point, or it will diverge, which means it will exceed any boundary. It will go to infinity. Right. So the interesting part here is then the set of convergent values. So black are the complex valued and therefore 2D points C, for which we have convergence of the sequence. So that's the convergence set. So here you can see the black area here. These are the C's for which this iteration converges. And the colors here, they come from the speed of divergence. So the faster the iteration goes to infinity, the more red in this case the color becomes. So for different convergence speeds you can just set different colors, and that's why you get this nice colorful picture. And the interesting part here is that this set of convergent values has this particular shape. It looks like an apple with a head, and that's why it's also called Apfelmaennchen or Apfelmaennchen in German. And yeah, this was invented by the mathematician Mandelbrot. And you can actually see that it's fractal in the meaning that you get similar shapes when you zoom in, when you actually do the zoom in. So here, I guess this piece was taken, and here you get zoom in, and you can see you get even more details. So the further you zoom in, the more detail you get, and the shapes that you get have similarity at each scale. And that's typical for fractals. So fractals have the so-called self-similarity, which means the shapes at any scale look similar. Yeah, so here more fractals. Fractals are based on self-similarity. You can also read more about it in this Wikipedia link, which means certain patterns appear at all scales of magnifications. Examples are coastlines, like when you look at the map of the world or any country or even a small area. The coastline always looks very rugged, no matter at what scale you look at it. Yeah, so they appear similarly rough in practically all scales. And this following picture shows the so-called Julia set, also from this time the German Wikipedia page on fractals. So here you have a nice picture of the Julia set. So it looks a little bit like the Mandelbrot set, but with different shapes. Yeah, another example based on a subdivision algorithm, which we will see more about later, is the so-called mountain fractal. Mountain because you can use it to model mountains or valleys. So here we take a straight line connecting 2 points as a baseline, like in the snowflake case. But now we go to the center of the line and create a new point by randomly offsetting it up or down within a certain range. So we have given a range, and in this range we create a random number at which we place this middle point up or down. And then we draw new baselines between the newly created points. So the endpoints stay the same, but now we have 2 lines connected to the middle point. And then we have the range for the offsets and begin the iteration at item 1 again. Right? We go back here and then we take the new baselines and do the same thing. So this is how it looks like. So here we can see we had a first baseline in black. Right here you have the control points at the end. Then we have this random offset within a certain range, and then we have new baselines, green. And for each of those green new baselines, we create another offset, which is now half as wide because we have a subdivision done. So we reduce this range. It doesn't have to be half as much. It could also be some other reduced factor. And this actually can help model different roughness. So here we have another offset and so on. And I have a little example here in Python, which we can take a look at. So Interp. So let me open my terminal window. First open the file in the editor. Okay. So here you can see it. So you can see again, I'm using OpenGL. I'm also using this random library from Python. And here you can see this function which creates this random shift. So as an argument we have the left point and the right point. So this plots the 2 points pt left and pt right and randomly shifts the middle point and calls itself on the new point pairs. So this is actually used for the iteration. Right, and here we can set a roughness factor here, 0.7. Here smallest distance basically tells the function when it should end, so that it doesn't go on for infinity. And here it plots the points. So here plots the left point and the right point. Here it computes the distance between those 2 points, because they can be any coordinate set, right? So point left, point right is a point in 3D. So here we can compute the distance between them. And if the distance is still larger than the smallest distance, we do the subdivision, which is here we are creating the middle point. So this is the average between the 2.5 of times the sum of the two. Then here we have a midpoint, and this midpoint is the distance times the roughness times a random number. So random gives me random numbers between 0 and 1. So if I subtract 0.5, then it gives me random numbers between minus 0.5 and plus 0.5. And you can see my factor here, which gives me the roughness, and here the scaling with the distance. So the more narrow the distance, the less offset we have. So here we take the midpoint and shift it by this random offset. Yeah. So then we have the same function here and calling it again. So here, see, we have this function name, and inside this function we now call this function again, but now on the two new straight lines that we have generated. So now from the left point to the midpoint and from the midpoint to the right point. Yeah. Right. So this basically is creating my offsets using a subdivision. Then here you can see the display routine, which is basically as we used it before. Here I have two starting points which I plot, and here I'm calling the display function. Oh yeah, here I forgot. Here's the function doing the iteration rand shift. That's calling this function here, and then this function computes all the intermediate points. So let's try. So Python 3. Yeah, so you can see it. So here this is just in 2D, right? Because that's how I programmed it. But you can easily also extend it to surfaces in 2D if you have a 2D grid. So each time I'm calling this function, we get a different shape. So you can see a new shape depending on the random numbers I get. So we have a valley, we have a mountain. So again, so each time it looks different. But each time we have the same starting and end point here at those two ends. So this works nicely, right? So you can use that to generate fantasy landscapes for computer animation. Okay, so back to the slides. Yeah, another example here for rough interpolation is the so-called Perlin noise. You can also read more about it in this Wikipedia link here. And this is based on the so-called diamond square algorithm. And here you can see the result. So this looks like, I don't know, like smoke or fire or something, or fog. So you can generate also different roughnesses. Left is a high roughness value and right is a lower roughness value. Yeah, so back to B-Splines. And from there we go to subdivision. So an important principle for B-Splines is that they share control points, which you can see here. So here we have our interpolated curve, Qi, and Qi is the ith section of the B-spline curve. So you can actually see that when we take a look at last time's example with a B-spline interpolation. So here our B-spline interpolation, remember we had those 4 control points, right, the red ones. And then this is the interpolated curve. You can see it's a fairly narrow stretch, a fairly narrow line here. So the line is not very long. It doesn't go much beyond the middle points. So this is the Qi here. So this Qi is generated then by using the spaces matrix and the control points here. And those control points, they are now shared between neighboring intervals, and this makes them C2 continuous and a smooth curve. So we could also see that when we take a look at last time's example, 2 interval. So here we have now 2 intervals, and you can see I added this this additional control point, and we can see we have 2 queues. So here there's the first line and here's the second line, and the connecting point here between them is called a node. Right, so this is a node here. Right, so these sections are defined as intervals between 2 nodes. Right, these qi. Yeah, and these adjacent sections, they share 3 control points. So we could just see, in this example, I just added another control point, but the previous 3 stayed the same for the second interval. Right. So each section is controlled by 4 control points, and neighboring intervals share 3 of them. Each control point influences exactly 4 curve segments, right, because of the sharing. And all points of a section lie on the convex envelope or the convex hull. Should call this convex hull of the control points. And basis functions, so this should be the basis functions, are affine invariant. So which means if you apply rotation or stretching or shifting, then you can as well do it on the control points instead of the final curve. Yeah, here's the difference to Bezier curves. You can see for Bezier we have 2 adjacent intervals which completely differ in their control points. So here we have the basis matrix for Bezier, and you can see here this is the first interval, has the control points P0 to P3, and the next one has P4 to P7. Right? They don't overlap, and that's why we can get kings and jumps in those curves if we are not careful. For B-Splines, for 2 neighboring intervals, we have 4 overlapping control points. So here we have P0 to P3, and here we have P1 to P4. So they share P1, P2, and P3. Right. Yeah, so maybe I can actually specify this here. 3 overlapping control points. And this makes the result smooth, C2 continuous and smooth curve. Yeah, so here's an illustration of a chain of control points. So we have different sections here, Q3, Q4, and Q5. And all the points stay the same except for P4, which is now plotted here for 3 different locations. And you can see P4 is shared by 2 sections, Q4 and Q5. And that means Q4 and Q5 are affected by the shift of P4. And you can see here Q5 changes, and also Q4 changes somewhat here in the end. Yeah, so we have connection points of the individual curve sections, which gives us m-1 nodes. So here those connecting points are the nodes. And in general the curve does not cross the control points, but a closer approximation is possible by repeating control points, which means we have the influence of the point is increased. So instead of having P0, P1, P3, P4, we have P0, P1, P2, P2, for instance. Yeah, so like here in the end, we have P5, P5, P5. So we actually have triple points. So for this last segment here, we have just P4 and then 3 times P5, and that's why the curve actually ended here. Yeah, so repetition of control points leads to a closer approach to the respective point, and also reduction of continuity. So here we have 2 points, so the curve comes closer, but that also means we only have C1 continuity and no longer C2 continuity. So the bend here is sharper, so it's less smooth here. Yeah, so right, this is the double point, and for a triple point we just have the G0 continuity. So here's the example, 3 times P3, that means the curve goes into this point and the next section goes out of it, but at a different angle, which means it's continuous in the function value itself, but not in the first derivative. So we don't have C1 or G1 continuity. Yeah, so we have a kink here. So a straight line on each side, but no continuity of the first derivative. Yeah, so this leads us to subdivision curves and surfaces, right? So this is a method for producing a smooth curve or surface by successively refining the geometry. So that's interesting because it gives us the possibility of having an object at different resolutions. So the refinement is achieved by adding new points and interpolating or moving existing points. And that actually gave the Oscar in 2006 for Ed McCatmull, Tony DeRose, and Joe Stem for improving subdivision surfaces. And that was integrated in the Maya system. And they should be a role model for media technologists. Right, and you can also read more about it here in the Wikipedia page about subdivision surfaces. Here's a little example for a line. So we start at a coarse representation with control points here, with a few control points, and then we refine the representation using more control points to get a smooth curve. And how that can be done is shown in the following slides. So the subdivision curves and surfaces are applicable to polygonal curves. Polygonal curves. So these are piecewise linear, and also to parametric curves via their control points. So we can have a refinement of the control points. And if you take the control points and make a polygon out of it, then you call it a control polygon. We can also apply it to polygonal areas. So I should call it polygonal areas. And also to parametric surfaces via the control polygons. The advantages in modeling is that we have an interactive refinement of the model, and it's intuitive in use, in usage. And also it has advantages in rendering because we have an automatic level of detail adjustment. So if an object appears small, we need less detail and can use fewer control points, which reduces the computational complexity. Yeah, so first is the Chaikin algorithm. So here basically we use cutting the corners of a polygonal curve. And repeated use results in a smooth curve, which you can read also more about it in this link. And here you can see how it works. So we have this curve, this polygonal curve, and then you just take the edges of the curve, the connecting lines here, and insert new vertices here, new control points, like in 1/3 and 2/3, and leave off the corners here. And then you get a new polygonal curve with more control points, automatically generated new control points. And you can see this iteration, if you continue it, will make it more and more smooth because we just cut off all the corner iteratively. So this is the mathematical formulation. So you take any given line between 2 points, pi and pi plus 1, then you insert new control points at 1/4 and 3/4 of the line. So this is QI and RI. So these are the new points now. And then you leave out the old ones. Right, so here you have QI and RI. They are computed like this. So you have a weighted average, which gives you those 2 points. Right, at 3/4 and 1/4 of the distance to the old points. Yeah, so here's an example. We start with this polygonal curve. Here we cut the corners. Here the distance 1/4 to the old corner. The old corner is then left off, and we have a more smooth version. And then if you do it iteratively, so for each new curve you apply it again. So the curves become smaller, or the line segments become smaller and smaller until it gets really smooth. So observe that we in this way get a smooth curve without using polynomials. So we don't need B-splines here at this point. We just do iterative refinement. So it's an alternative approach to obtain smooth curves. Here another example. So same approach, 1/4 from each point. We have new control points and then draw new line segments between them. So we have new edges and new vertices. And each time we do another iteration, it becomes more smooth until we have this really smooth curve. Yeah, and this Chaikin algorithm can be applied not only to the polygonal curve, but also to parametric curves such as B-splines by applying it to the control points. The procedure again, we have a refinement of the control points according to the algorithm of Chaikin. Right, so here you can see an example. So here for simplicity, I took a quadratic uniform B-spline curve instead of a cubic. Right, what we saw so far is a cubic B-splines with a 4x4 matrix. Here we have a quadratic B-spline with a 3x3 matrix, basis matrix. So here you can see the basis matrix of the quadratic B-splines. So here is the formula for the quadratic B-splines. Since it's quadratic, we only have the maximum exponent of u being 2, so u square. So this simplifies matter somewhat for this example. So here we have 3 control points. So here we just have 3 control points because it's quadratic. And here you can see the resulting curve, which is generated by this example B-spline. Yeah, so now we can combine it with Chaikin, right? We have a refinement of the old control points P1, P2, P3 using the Chaikin algorithm. So here we can see the Chaikin algorithm. We have the old control points P0, P1, P2, and you can see the rule 3/4, 1/4. So these are the weighted averages, and this gives us the new control points in the next generation. So here the superscript gives us the iteration number. Yeah, and if we put this into a matrix multiplication, we get the formulation here on the right hand side. You can see here this factor 1/4 appears everywhere, so we can factor it out. The p's appear everywhere, so we can factor them out. And this is the resulting matrix that we need to obtain the new points. So you can see here we start with 3 control points, and after Chaikin we get 4 because we have 4 rows here. Right? So Chaikin gives us 1 more point for each iteration, for each segment. So question, how do the resulting quadratic B-spline curves for the old and the refined new control points differ? Right, so we can make a spline curve, quadratic B-spline curve, using those 3 control points, and then we can make another one using those 4 points. So here we actually get 2 segments, right, because we have 4 control points. So for the first three we get the first segment, and for the last three we get the next segment. Yeah, so we are curious if the new ones look better, right? So for that I just took an example and wrote it in Matlab or Octave and also in Python. So here you can see the function quadratic B-Spline. It takes as an argument our helper variable u, which is between 0 and 1, and then our matrix of control points P. Right, so P contains the coordinates of our 3 control points. Yeah, and then the basis matrix here is given. M is the basis matrix. Here we have the vector of the exponents of u. And here you can see the generated interpolated value for the given u. So we have uVec times basis matrix M times control vector control point matrix P. So fairly simple. Then I have another function for the Chaikin subdivision. Given the control points P. So we have two-dimensional control points in matrix P. So dimension 3 times 2. So we P contains 3 control points, and it should output 4 control points. Yeah, so here we can see P consists of the coordinates of the 3 control points. Here R is this matrix for the Chaikin subdivision, and here we do the multiplication R times P, and out comes Q, which are the new control points. So Q should now contain 4 control points corresponding to the 4 rows of this matrix. Yeah, here I have a Matlab or Octave script to create a plot. So here I'm taking some points. Right, you can see the coordinates of 3 points to start from. Then I have this spline interpolation. I'm using 20 points for my variable u, here 1/20 times n, using the 3 control points here, and then I'm plotting the resulting points with a star. Then I apply the Chaikin subdivision here and plot the result. Yeah, here are the new points. Right. And right. And then I'm applying the quadratic spline. Here you can see the function quadratic spline, which I just defined. Here I apply it to the first 3 points, and here I apply it to the last 3 points. And then I'm done, basically. And then we can compare it on the same plot. Here you have the corresponding script in Python. It's a little bit small, so it's easier if I just open it here in the editor. Oh yeah, there's still this window open. So if I take this example, gedit Chaikin B-Spline, you can see what it's doing. So again, here first I define this function for the quadratic B-Spline. Here the basis matrix of the B-Spline, here the u vector with the different exponents, and here you have the product of the u vector times this matrix M, the basis matrix. And finally, here you have the output of the B-Spline interpolation with a product between our Q, here the multiplication of the 2 multiplied with a control points P. Right, so here we have the multiplication of those 3, and then we return it. here we have the Chaikin subdivision function. Here you can see the basis matrix for the Chaikin subdivision, and here we do the multiplication to create 4 new points. And here I'm doing the plotting. So here I'm having my start points P. So I have 3 starting points. Here are the coordinates x and y. Here I plot them. And here I'm doing the interpolation using 20 points for each segment of the spline. So here you can see the spline for the P's, the original points. Then I'm doing the subdivision. I get the new points, plot the new points, and somehow there should be another quadratic spline interpolation, which I don't really see here. Okay, let's try what it's doing. So Python 3. Yeah, looks good actually. So here you can see blue are the connecting lines between the original 3 control points. Here 3 points connected by 2 lines. And red are the lines after Chaikin. Right. And then you can see here the stars coming from the different B-spline interpolations, and they're actually on the same, always on the same line here. So you can also see a similar result using my Matlab example. Here you can see the starting points and their connecting lines, control points here. Then here red, you can see the connecting lines for the new control points after the Chaikin subdivision algorithm. And here you can see star and circle are the B-splines before and after Chaikin algorithm. And you can see they lie on the same curve. So before and after gives you exactly the same B-spline curves. So that's kind of disappointing in one sense, because it shows you that applying Chaikin to the control points doesn't make any difference for B-splines. So here you can see it doesn't change the resulting B-spline before and after the Chaikin subdivision. But it also tells you if you continue the Chaikin algorithm, you will get B-spline, quadratic B-spline interpolation. So this is actually a different way to obtain quadratic B-spline interpolation. And it might be advantageous to use this instead of the polynomial computation. Yeah. So this refinement can be continued, and the control points converge to the quadratic B-spline curve, which remains the same regardless of the further refinement of the control points. Right? Important point. The curve resulting from the refinement of a polygonal curve according to the Chaikin algorithm converges into a quadratic uniform B-spline curve. So you can see it here. So here, first refinement, second refinement. So it comes closer and closer to the quadratic B-spline. Yeah, and this not only works for the quadratic B-spline, which was just a simple example, but also for the cubic B-splines, just with a different subdivision. Right? We have a similar process for the cubic B-splines. The difference is only the new control points are located on the middle of an edge of the control polygon. So here you can see it. So the P's are the original control points, and now we have middle points which become new control points. And near the corners of the control polygon, we're cutting off the corners similar to before to obtain vertex points. So here we get new points here too. And both edge and vertex points are determined by halving the length of the edge. This gives us an efficient calculation for the cubic B-splines. Yeah, and here's the corresponding matrix for this type of refinement. So you can see we get input is 4 control points. Control points are the vector or the matrix from the right hand side, so we have 4 control vectors, and out comes 5, right? So this is what we see here: 4 control points before and 5 control points after. Right. Yeah, so you can see it a little bit more closely how you can obtain the edge points V. So here you also start at the middle points of the new edges and connect them, and on that middle you get a new vertex. You have a new control point here at the V. Yeah, so this is actually a very practical thing for computing smooth interpolations. Okay, yeah, I think this is where we should stop today. So thank you for your attention, and then see you next time.